Hi there, my name is Ryan with Web FPGA. This is a brief introduction to FPGAs in the world of hardware description. If you don't know what any of that stuff is, that's fine. This video is going to break it down for you. In this video, I'll be going over two separate examples, the first one being PWM and the second one being image manipulation. If you're not familiar with PWM, that's fine. We'll go over that in the next couple of slides. Okay, PWM. PWM stands for pulse width modulation. I'm going to break down what those words mean. Pulse is talking about these little bumps right here. These are pulses of the signal. Width is talking about the width of the signal right here. And modulation is talking about the change in this width. PWM is useful for a couple of reasons, but the main one is controlling things of varied intensity. For example, you could control the brightness of a light bulb, or you could control the speed of a motor. Now imagine this, you're standing in front of a light switch and you turn it on for 1 second, and then you turn it off for another second, and then you turn it on for 1 second, and then you turn it off for another second. In essence, the light bulb is on for half the time. Now, with a 1 second delay, it kind of just looks like it's going on and off, on and off. But if you did this 1,000 times a second, or 10,000 times a second, the light bulb would look 50% on. It would look dim. So when I see a light bulb here that's 25% on, what's really happening is a computer is going up and down, and it's leaving the light bulb on for about 25% of the time. Now, most microcontrollers have built-in hardware timers, which can be used to create these PWM signals. Typically, they have 1 or 2 timers, and those timers are hardwired to pins to produce these signals. Usually, you can also implement this in software. However, this can have drawbacks, such as latency, too much resources. We'll get to those in a second. In the next couple of slides, I'm going to use the Arduino as an example of some hardware that has built-in PWM. Now, this microcontroller has timers that are connected to pins 3, 5, 6, 9, 10, and 11. These are all pins that you're allowed to use the hardware PWM. Now, to use this hardware PWM, you use the directive analog write right here, and you simply put down the pin you want to write to and the value. And now in the background, the hardware is going to output whatever signal you requested, and you won't have to have a loop or anything. It's just going to do that. So next we're going to talk about how you might implement this in software if you couldn't use one of these pins. Implementing PWM in software can have a lot of benefits. It offers flexibility because, say, I can use pin 13 instead of one of the hard-coded pins that the Arduino Uno offers. All you have to do is write a simple loop with a counter and have some condition that determines when to turn your pin high or low. In this case, we're having all even numbers high and all odd numbers low, which will create a waveform that looks something like this. Now, looking to this example, if we have something that checks for every 5th number, well, that's just 1 over 5, which gives a 20% duty cycle. And likewise, this one is 80% because it is 1/5 low, while this one is 1/5 high. When it comes to implementing multiple PWMs in software, the technique is pretty much the same. We have our main loop with our counter, and as our loop goes through each statement one by one, we have if statements right here that determine when to pull our pin high or low, which creates the PWM ratio that we want. Now, the important thing to note here is that each PWM signal is created one by one. So, basically, PWM 5 won't be updated until 4 is updated, which won't update until 3 is updated, till 2 is updated, till 1 has updated. This is fine for a small amount of PWMs, but if you had a lot, eventually you would run out of resources. And this makes even more sense when you're doing serial writes or sensor reads, things you would normally do on a microcontroller. So all of these statements are executed sequentially at 16 megahertz, which is the clock rate of an Arduino Uno. Now, when we look at Verilog, which is a hardware description language, you write code by declaring how you want the hardware to look. So for example, here, this 8-bit counter, first we're declaring an 8-bit register to hold our counter state. But the cool thing to note here is that if I wrote reg, let's say 10:0, that would have been an 11-bit counter, which is really cool. You're declaring the actual bit size of the register that you want. So you can have 11-bit counters, 17-bit counters. If your number only goes to so high, you can make it that many bits. This is useful for, say, like if you have a state machine that has 8 states, well, you should make that 3 bits. It's very efficient. This is unlike microcontrollers, because on a microcontroller, your integers and bytes and such are typically only 8, 16, or 32-bit values. This is set by the architecture of the chip. It's baked into silicon and you can't change it. But with an FPGA, you can come up with whatever you want. So this section right here is the main counting section. So it's going to take the clock that comes in like this, and on the positive edges, so the rising edges right here, it's going to increment the count by 1. This is equivalent to this increment right here. Now, the cool part here is that all these assign statements are declarations of combinational logic. So these are statements of fact. This is going to be true always. It's saying, as long as counter is divisible by 5, then we're setting LED 1 high. As long as counter is divisible by 4 evenly, then LED 2 is high. Now, all of these operate on the exact, they all operate at the exact same time. So if counter ever changes, then these all change. This is a lot different than the microcontroller, where, let's say, PWM number 5 never actually occurs until all of these have occurred, because the microcontroller operates in this fashion. It's one big loop. That's the benefit of hardware. This next example is going to illustrate how FPGAs can be useful in the area of image manipulation. Now, what's cool about this example is that you can understand it if you're coming from a pure software background. You don't have to understand PWM or Arduinos or blinking LEDs or microcontrollers or any of that. If you know how to code, then this example is going to make a lot of sense. So the thing to note about images before we get started is something like this is really just a grid of pixels. This grid in particular is a 10 by 10 grid of RGB pixels. And if you're curious, this grid right here is actually this subsection of the cat's eye right here. Before we dive into image manipulation, it's important to understand how computers represent images. Each pixel is a combination of the intensities of red, green, and blue. Now, the intensities are measured from 0 to 255. And the reason for this is because each pixel is 1 byte, and each byte equals 8 bits. Now, if we take 2 to the 8th, we'll get 256, which is how many possible combinations, or how many possible different intensities there are, which gives us the range of 0 through 255. So separating that grid of pixels into separate grids for each color, we get red, green, and blue. And we can take, for example, this one right here, which describes very low intensities in terms, or in regards to the first pixel right here, and it's very dark. We have 80 for red, which is this one right here. If it was 0, that would mean black. If it's a very high number, like 222, it's going to be a very intense red, such as right there. You can say the same thing for the other colors. We have this one, which is about 60 for green, which is very dark, and this one is 44 for blue, which is like almost non-existent. It's so dark. So yeah, that's how pixels are represented in computers. Moving forward. So one example to go over is if we just want to tint the image red. So you could see that if we wanted to tint the image red, we might say take each pixel, so this value is 222, and if we want to tint it red, we would add 10 to that value. So this would be 232, and we would take this value and we'd add 10. We take this value and we'd add 10. This one and 10. And you do that for every single pixel. And then when you merge the RGB palettes together again, you will get a redder image. Now, how would you accomplish that in software? Well, you might see your image as a 10 by 10 array of pixels, and each pixel can be 0 through 255. And you would write a simple for loop that goes through all 100 pixels, and it adds 10 to the value. That's tinting the image by 10. Continuing along the same line, if we wanted to brighten the entire image on every color instead of just tinting it on one color, we have to loop through each grid and increment each one by the amount that we want on the intensity. So looking back here, if we have our 3 grids for our 3 colors and we write a simple for loop that goes through each one and adds 10 to the intensity for each color, red, green, and blue, that's how we accomplish our task. But the thing to note here is that we're looping 100 times. Now, if you loop 100 times, executing 3 statements each, that's going to lead to a total of 300 statements. Now, you have to note that this is a simple 100 pixel grid array, but when you're dealing with a 10 megapixel image, this is going to take maybe a second or something. But a GPU or an ASIC or an FPGA, these can all execute this type of code very quickly. And in the next few slides, I'm going to show you how you can accelerate that process. Now, we can accomplish the exact same goal in one clock cycle using an FPGA. This is a crude implementation, but it demonstrates the point. Basically, what we have going on here is we have all of our red, green, and blue pixel grids represented in an array of registers, and we have our output wires right here, and we have our module that does the digital logic necessary. All this module does is take our input right here and our output here and connects them in a way that the output array is the same as the input array, but for each element we're adding 10. Now, when this program, when this Verilog goes through synthesis, it's going to generate the digital logic necessary. This might be a full adder or a lookup table, or however the synthesis engine best determines to do it. And it's going to create this logic block, and when the FPGA runs, it's going to do all of this at the exact same time. So effectively, it's doing it in less than one cycle. It's pretty cumbersome to write an assign statement for each pixel in the array, so we've written a generate statement that produces each assign statement for us. But the important takeaway here is that this is not very idiomatic code, because adding 10 to each pixel is not an entirely useful function. This example is just created to show the highly parallel nature of Verilog, and that with something as short as this, you can modify the contents of 100 pixels in one cycle. Well, that brings us to the end of our presentation. Thank you for watching. If you'd like to learn more about FPGAs, visit our website webfpga.io. We have just launched our first development board, which has over 30 GPIOs and an onboard RGB LED. There's also an onboard microcontroller, which you can program with whatever you want. But the main selling point is our Cloud IDE. All you have to do to program the board is plug it into your computer via USB. You don't have to install any drivers or any software. You can just write your Verilog right here, hit synthesis. It'll take a bit for it to synthesize, and then you can hit flash, and then it's going to flash, and then it's running your code. It's very cool stuff. Please check it out. Thank you for watching.